work? Work, in the simplest of definitions, is just a force times a distance, right? So it's a force that you're applying to something, and over the distance that you're applying it, right? It's very simple, and although this definition is very, very simple, it's absolutely true. Unless your force is not constant. If it's constant, then this definition is absolutely true. It's just the force times the interval that you're applying it over. But if your force is variable, then you can't really use this definition. So to mitigate this problem, what we say is, okay, I'm not going to calculate the work over this really long interval during which my force is changing. I'm going to shrink that interval and make it so small that the force is actually constant over that interval. Okay? It's a very, very common theme throughout calculus. So what we do is take the delta x, convert it into dx, and say, now my interval is really, really, really short, and my f is constant over that interval. So now I can actually use this formula and say the infinitesimal amount of work is the force at that interval times the infinitesimal interval. Okay? Now if I want to find the total work, which is usually what you're interested in, you're going to sum up over all those infinitesimal amounts of work, and then you can use this formula to replace dw with f of x times dx to be able to actually do the integral, right? So again, it's not hard. It's just this process is a little it could be a little mind-bending as to why we do it or how it works if you've never seen it before. So let's go ahead and do an example to see how this process is carried out for a real example. So here we have a bucket of water, and we're pulling it up 20 meters, and we're interested in knowing how much work we're doing. Part A, it's basically just the water and the bucket and the rope. And part B, we're going to add another constraint that's going to make it a little a little more fun. So for part A, we're asked, well, what is the work if the water weighs 20 kilograms, the bucket weighs 30 kilograms, and the rope weighs 2 kilograms per meter? Okay? All right, so we don't know off the top of our head. So what we're going to do is break up the problem into smaller problems. So we're going to say the total work is just the work done on the water plus the work done on the bucket plus the work done on the rope. And then we're going to do these guys individually and then add them all up. Okay? So what is the work done on the water? Well, I don't know. We go back to our simple definition, see if it applies. Work is force times the distance. If and only if the force is constant, right? Well, in here, the water, what is the force that we're applying to the water? Well, the force is just mg, right? It's the force that's counteracting gravity to pull this thing up. Well, is m changing? No, the water's mass is staying constant. So m is constant. Is g changing? No, g isn't changing. So the total force is not changing. So this definition applies. We can totally just easily use that definition and say, well, the work is just mg times the interval that we're pulling it over. So what is m? M is 20 kilograms. What is g? We're going to say g is 10 just to make our calculations easy. And then what is the interval that we're pulling it up over? It's the 20 meters, right? So 20 meters. I'm going to actually put my units here as well. So at the end, we're going to have 20 times 10 times 20, or 4,000 Newton meters. That's the unit of work, one of the units of work. So what's the work done on the bucket? Well, it's going to be very similar. The bucket, again, the mass isn't changing, g isn't changing, so it's just going to be the mass, or 30 kilograms, times g, which is 10 meters per second squared. And what is the interval? The interval is the same. It's just 20 meters. Right, so 30 times 10 times 20, or 6,000 Newton meters. Okay. So what about the rope. Now the rope is a little different. Why? Because as we're pulling up the rope, we're pulling some of it, and now we don't have to carry that weight anymore. We don't have to pull up that weight anymore. So the weight of the rope is actually changing, so that by the time we get to the end, all the rope has been already pulled and we're not pulling anything, right? So we have to somehow account for that. And we're going to do it very simply. First of all, we're going to do it actually the way we do all variable forces. We're going to ask ourselves, well, what is the force at the beginning? Okay? Well, force is always mg, right? G isn't changing. M is the only thing that's changing. So in the beginning, M is going to be, got to think here, what is the weight of the whole, or what is the mass of the whole rope? Well, it says the rope weighs 2 kilograms per meter, and the rope is 20 meters long, right? So it's just 40, 2 times 20. And now you got to figure out, how is it decreasing? How is it changing? Well, we have to make the realization, or make actually the assumption, that we're pulling this thing linearly, right? So now we can say, well, at first it's 40 kilograms, but for every meter, that we pull up, we're decreasing the weight by 2 kilograms. So for every meter that we pull up, we're going to decrease it by 2 kilograms. So it's 2 times x, where x is how much you have pulled up. If x is 10, if you've pulled it up 30 or 10 meters, then you've decreased its weight by 20, right? So that's going to be our variable force here, all right? So now we can go back and compute the work now that we know the force. Remember, we can't use this formula anymore. Why? Because the force is changing over our interval. So we have to go to the calculus definition, right? And it's the integral of the force times dx. So the integral of the force, which is just 40, minus 2x dx. And what is our interval? Well, we're starting at 0 and going up to 20. That's it. Right? And again, it's very simple, very succinct. The only thing that you really have to remember is once you get all these 3 components, you have to add them up to get the total work. We're not going to do that because that's just arithmetic, and it's a waste of time. But on the test, you should, because it's usually worth points. So now let's do part B. All right? Part B says it's got a new condition that makes it a little different. It says water is pouring out at 1 kilograms per second, and we are pulling the bucket up at 3 meters per second. Okay. Now let's think about what that actually says. It's giving us a rate at which the water is pouring out of this thing. That's useful, but not really. We can't really use that directly. Why? Because our integral the integrals for work are always going to be in terms of distance, in terms of x, in terms of y. They're never going to be in terms of time, because that's just not how work works. So the way we have to mitigate that problem is somehow figure out, how is this water pouring out related to distance, not time, but distance. And they actually give us the solution right here. They tell us, oh, well, we are actually pulling it at 3 meters per second. So for every second, you're pulling it up 3 meters, okay? And that solves our problem, because we can't use 1 kilograms per second directly into any sort of any formula that makes sense, because it's in terms of time. We can't deal with time. It's a distance. It's a distance integral. So we're going to say, all right, well, I'm pulling it, or water is pouring out, rather, at 1 kilograms per second. And for every second, I'm pulling it 3 meters. Okay? So then that leads me to believe that for every meters, 1/3 of a kilogram of water is poured out. Okay? Does that make sense? we started with the ratio of kilograms per second, and then said, okay, well, we don't know, I don't care how fast in terms of time this thing is pouring out. I want to know in terms of distance. So then we add the seconds over meter, units cancel out, and we're left with this guy. So that's our the rate at which water is pouring out. Again, we're going to do the same thing we did with the rope, and we're going to say, well, the mass of the water in the beginning used to be 20 kilograms before anything was poured out. Now, for every meter that we go, 1/3 of a kilogram is getting poured out. If you can look at the units, you'll see there's a kilogram per meter here, and there's a kilogram here. So we need a distance here to mitigate the unit problem that we have, inconsistency that we have, and we can solve that by putting an x here. And it makes sense if you think about it. We're saying we start with 20, and then we're going to multiply the rate at which the water is pouring out by how far we've gone. So if we've gone 6 meters, 2 kilograms of the water has been poured out, and so we're going to have 18 kilograms left. Okay? So we can actually finish this problem by saying, I'm going to go ahead and erase this part. So by saying, okay, well, this is my variable mass, then my work for the water is going to be, again, mg, work is always going to be f times dx. So the integral of f times dx. Then I'm going to say, well, my f is just this thing times g, right? 20 minus 1/3 x times 10 for g dx. And that goes from 0 to 20 again, because our bounds haven't changed. And that's the work that you do for the water. Again, this would replace this, and you would add it up to these two, and there you have it. It's very easy. It's not hard. Work is really not a hard concept. You just have to really be careful with when you use the constant definition and when you use the calculus definition. If your force isn't changing, no need to use this guy. You can use the simple one. If it is, then you have to figure out how to write your force. In other words, how is it changing? And then actually do the integral and get your answer. So there you have it. That's work.